compressed air systems.
Hello and good afternoon, everyone. Today we're going to present a short guide to greener and more efficient production. So we're going to look at some techniques and suggestions that you can apply to your industrial processes that will hopefully make them more efficient, hopefully make you a little bit more profitable, but also make your production process a little bit more greener. My name's Oliver Kent, and I will be talking about compressed air systems. My colleague, Jason Chapman, joining us today, will be talking about industrial process cooling. So today's presentation is brand neutral. So a lot of the techniques and products that we'll be looking at are available from a number of manufacturers. With that in mind, I'd just like to take a minute to introduce the organization that Jason and I work for, and that's Atlas Copco. Atlas Copco is a multinational engineering company. We have a presence in about 180 different countries. We've got a turnover of approximately 15 billion euros a year. We are fairly long-standing. We were established in 1873, and we've got a Swedish heritage. So our head office is still in Stockholm. Atlas Copco really focuses on industrial equipment, and to do that, we're split into 4 business areas. So working from left to right on the pictures along the bottom of the screen, we've got vacuum technique, which basically develop all things to do with creating vacuum technology. We've got compressor technique, and then we've got industrial technique, and industrial technique really focused on production tooling. And then finally, we've got what we call power technique. And power technique is really focused on mobile equipment. So things like mobile lighting towers, mobile generators, but also mobile compressors. Jason and I work for, we belong to compressor technique. So that's in the highlighted box. And compressor technique focuses on compressor and gas technology, but also industrial cooling process technology as well. So if we have a look at my chosen subject, which is all about compressed air generation and compressed air systems, and I'd just like to give you some brief facts about the energy consumption that goes into making compressed air in the UK. So if we start from the top, industry uses approximately 30% of the UK's electricity consumption. Of that, about 10% of the UK's industrial electricity consumption goes into making compressed air, so generating compressed air. So if we do the maths, simple maths, you can work out that compressed air generation accounts for approximately 3% of the UK's total national energy electricity consumption. So if we put that into numbers, the last figures I've got are from 2022. So in 2022, compressed air generation consumed approximately 8,500 gigawatt hours of electricity. So that's a big number. So if we put that into some context, in 2022, Sizewell B nuclear power station generated approximately 10,357 gigawatt hours of electricity. So we can see that in 2022, compressed air generation, on average, consumed more than 4/5 of Sizewell B's annual output. So we can see that generating compressed air takes up a very large amount of energy. And with that in mind, if we have a look at the total cost of ownership of a compressed air system, we see that energy consumption over 10 years, the cost of energy is over 3/4 the amount of the total cost of owning a compressed air system. And if we want to, of course, we we all want to become more profitable, and one way to become more profitable is to drive down costs. And if we want to drive down the cost of ownership of a compressed air system, we can look at potentially doing three things. We could look at maybe reducing the investment, reducing the capital cost, reducing the maintenance costs, and of course reducing the energy cost. Now, it's actually quite difficult to reduce the maintenance and investment costs. Those costs are fairly fixed. And even if we could reduce either of those costs by a substantial amount, if we, for example, reduced our maintenance costs by 10%, actually 10% when it comes to the maintenance costs, when we look at the total cost of ownership, that is only a very small reduction of the total cost of ownership. So if we want to make meaningful savings when it comes to owning a compressed air system, we really need to focus on the energy costs. And really, energy efficiency has become the main driver of R&D in compressed air systems. So virtually all the R&D is focused on reducing the cost of reducing the amount of energy consumed by compressed air systems. So if we look at that, how that applies in the real world, so if we take a typical medium-sized industrial user of compressed air, typically they would have an installed compressor power of about 110 kilowatts. They might run 2 shifts a day, so you're looking at about 4,000 hours a year of operation. And let's assume that you could save 20%, if you could improve your compressed air system to give you a 20% energy saving. And that's actually not very unrealistic. If you have an old compressed air system, if you repair the leaks, if you remove the bottlenecks in the compressed air pipework, if you invest in new capital equipment, you would expect to have approximately a 20% improvement in its energy efficiency. So what does a 20% improvement in energy efficiency look like? Well, over 10 years, that would give you approximately a £220,000 saving over 10 years. You'd probably be looking at a return on investment of about 24 months. After that 24 months, everything you do after that is basically saving you money and hopefully going back onto your bottom line. There are various, you'll find that on the internet, there are various estimation tools that can help give you a sort of a ballpark figure of the sort of savings that you can achieve. One of those is our own Atlas Copco estimation tool. Also tied in with that is the carbon reduction as well. So as well as looking at how much energy and money that we'd save, we also look at how much carbon, how much we're going to reduce our carbon footprint. So we've seen that energy savings are possible, and we've seen that if we can make energy savings on a compressed air system, there can be big benefits, not only for our bottom line, but also for the environment by reducing the amount of energy that we're consuming. So how do we actually achieve those energy reductions? What can we practically do to improve the performance of our compressed air system? And Atlas Copco has created a 10-step guide to creating or to refining, to improving your compressed air system to drive out as much inefficiency as possible. And today we're going to look at 5 of those topics. So we haven't got enough time today to cover all 10 topics, but what I'd like to do today is highlight and really just sort of go over 5 of those topics that I think could be applied by yourselves in a reasonably short time, but also for sort of fairly modest capital outlay. So the first thing we want to do is to understand our compressed air usage. And if we take a typical industrial compressed air system, we actually find that out of all the air that we're producing, only 50% of it actually goes into our production process. And effectively, the other 50% is wasted. And this is in a typical compressed air system. So we'd lose approximately 25% in leaks. We would lose approximately 15% in what we call artificial air demand. So this is where we're potentially running our compressed air system at too high a pressure, or maybe we're over drying the air. and then approximately 10% would be other losses. So other losses could be a production machine that, when it's shut down, isn't isolated from the compressed air network and is still using compressed air even though it's not working. Also, inappropriate uses of compressed air. Maybe there's devices that are using compressed air that could use another power source. So you can see, out of our total 100% air generation, approximately only 50% of it actually goes into useful production. So when we look at our compressed air system and we look at the performance of our compressed air system, what are some simple activities that we can undertake that basically improve the performance of our compressed air system? So one of the most obvious things we can do, one of the most obvious activities that we can undertake, is to implement some sort of leakage detection process. So the more we can reduce our leaks, obviously the less air that we have to consume. So as we saw before, on average, 25% of our compressed air is lost to leakage. And when we look at how much air is lost through leakage, well, working at 7 bar, which is a typical compressed air system working pressure, a 3 millimeter leak is the equivalent of running a 5 kilowatt compressor day in, day out. A 6 millimeter leak, still not a very large hole, is the equivalent of running a 15 kilowatt compressor day in, day out without any benefit to your production. Then we go on to production equipment. Now, a lot of production equipment uses compressed air, but a lot of production equipment, even when it's not running, will still allow compressed air through it. So it would still leak compressed air. So one thing we can do is to isolate production equipment when it's not in use. Isolate that production equipment from our compressed air net. Then we could do an audit on the working pressure of our compressed air system. Do we need to be running our compressed air system as high as we actually run it? Could we reduce our compressed air system average pressure by half a bar? Could we even reduce it by 1 bar? And for every bar pressure reduction, you will reduce the direct energy consumption of your compressed air system by 7%. So not an inconsiderable amount. But also, as a side effect, by reducing your working pressure, you reduce the amount of leakage as well. So by reducing your working pressure by 1 bar, you will reduce your direct energy consumption by 7%, but you will reduce your leakage by a further 13%. And then finally, keep your compressed air, your compressor room cool and clean. Keep your compressor room cool. Compressors are a lot more efficient and work a lot better when they're kept in a cooled environment. But also, please keep your compressor room clean. You've got an awful lot of ambient air going through a typical compressor room, and a lot of that ambient air has got dust in it, which will eventually collect on the intake filter of your compressor. For every 3 millibar pressure drop over your compressor intake filter, you will increase its power consumption by about 1%. And then finally, today's tip, when it comes to looking at compressed air, when you're looking at your compressed air installation, before investing any serious money in updating, revamping your compressed air system, first do an audit on your compressed air system. Look to eliminate the leakage first, look to eliminate the waste first, do an audit on your working pressure, because you might find you actually need your compressed air system actually would function with a smaller compressor. So instead of being a 110 kilowatt compressed air system, you might actually find by the time you've done an audit on your compressed air system, by the time you fixed all the leaks, by the time you've reduced its working pressure, instead of a 110 kilowatt compressed air system, you might actually have a 90 kilowatt compressed air system. And then you can invest in the capital equipment accordingly. Conduct a review on your airnet design. A lot of airnets in industrial facilities have grown organically, so they've not necessarily been planned in the best way. So typical compressed airnet will have a lot of dead ends. It will also potentially have a lot of bottlenecks, nodes where the compressed air can only go through one point of pipe work. a little bit more capital outlay required. But if you find you've got a compressed air system with a lot of dead ends, look to do a review and see if there is an easy way you can turn your compressed air dead ends into a single loop. By turning your one-way compressed air system into a loop, you give the compressed air effectively two ways to get to the point of use, massively reducing the amount of pressure drop. And as we saw, if you can reduce the amount of pressure drops in your compressed air pipework, you can potentially reduce the average working pressure of your compressed air system and therefore make the direct savings on the electricity and the indirect savings on your leakage. Also, when it comes to distribution and your compressed air network, don't forget the volume of the air network. As a general rule, the larger the volume in terms of bufferage that you've got there, the better. So when it comes to air receiver sizing, the bigger the better. It's a simple rule. So why the bigger the better? It basically gives the compressed air controllers more time to react to what's happening in the compressed air system. When you look generally on a typical compressed air system, when you look at demand over time, it looks like the Himalayas. It's very variable. And so a compressor controller has to react to that constant changing in load. By introducing a larger air receiver, you slow things down. You add a lot more hysteresis to the system, and it gives the compressor controllers a lot more time to react to the changes in demand, your compressed air system. Also, if you've got fixed speed compressors, you will reduce drastically the amount of unloaded running time. If you've got variable speed drive machines, then you'll find that the variable speed drive machines have got a lot more time to react to changes in the flow. We mentioned about getting an audit of your compressed air system before you do any major capital outlay. And one thing you can do is get an audit on the usage of your compressed air. What type of flow profile does your process have? And typically compressed air usage profiles fall into three bands. Working from left to right, by far and away the most common type of compressed air profile is the variable flow profile. Basically, this is a situation where you've maybe got a lot of different production machines all randomly working at different times, so that your air demand is actually very variable. Less common is the steady flow. The steady flow air profile is a lot more common to very large industrial processes. So, for example, a car manufacturing plant where they have a steady demand for compressed air. And then finally, you've got the variable flow based on a shift pattern. So in this case, you'll have potentially a variable flow, but you might have that then based on a shift pattern, so shift between day or night. So you will have a very large variable flow during the day with a smaller flow during the night, or maybe during the week and at the weekends. So a larger demand at the week during the week, and then a smaller demand at the weekend. You're still doing production at night, or you're still doing production at the weekend, but you've got a smaller demand. And your flow profile will determine the type of technology that you want to invest in. So if we look at variable flow profiles, probably the best solution for a variable flow profile would be a variable speed drive compressor. Less common is the steady profile. Well, the most efficient way of meeting that big base load is using a fixed speed machine. But if you've got a variable flow based on shift patterns where you've got a very large steady flow rate you need to meet, well, then a combination of machines might be the best option for you. So always get an audit of your air demand first before making any investment into compressed air technology. And then system controllers. Okay, so we might have a compressor room with several compressors in it. Ideally, we don't want those compressors all just running independently, doing their own thing. We want to pull those compressors together under a single controller so that our compressed air system is running as one coherent system. And we've got here an example of the sort of performance benefits using what we would call a central governor. So a central governor is quite a sophisticated compressed air controller, and a central governor is designed to control multiple compressors, but of differing sizes. So if we have a look at our different flow profiles, we've got a range, we've got 4 different flow profiles that a large industrial user might experience during the week or during the month. And then we've got underneath 2 different scenarios of controlling those compressors. The top scenario with the red dials is where you don't have a central compressor room controller, and then the bottom profile is where you do have a central compressed air, a central compressor room controller. So you can see that we've got a very varied flow profile. And if we don't have a compressor room controller, we can see that the selection of compressors to meet the demand is based just on either what we call cascade, which is a very primitive form of compressor system controller, or using a simple sequencer. And we can see that because of our varied flow profile, we don't always get the best machine to meet demand. When we introduce a compressor room controller, if we a central governor, for example, we can see that a central governor takes all the compressors available to it and will then select the most suitable compressor available to it to meet that real-time demand. So if we got a low flow demand, instead of just selecting the next machine in the sequence, which might be the large machine, the governor, the central controller, will select the most appropriate machine for that demand, which might be the smallest machine. If we've got a higher demand with a variable flow, the best solution there is to have a large compressor to meet the base load with a smaller machine topping up. If we've got a large steady demand, then the most appropriate compressor might be the single large compressor. And then finally, if we've got a very variable flow, then the 2 smaller machines working together might be the most appropriate solution to meet that compressed air demand. And that's why on virtually every compressor system with more than one compressor, you really want to think about investing in a system controller, because as well as the efficiency, when we look at efficiency, we're looking at compressor design, we're looking at the sort of, can we save 1% here, can we save 1% there in fine-tuning our compressor designs to make them as efficient as possible, but also control plays a huge aspect in making our compressed air system run as efficiently as possible. And then my final slide, and I've kind of saved the sort of the best till last, really. Now, energy recovery. So when we compress air, we generate a huge amount of heat. Yes, we generate compressed air, and all that power in the motor goes into compressing the air, and we get compressed air, which is great. That's what we want to achieve. But as a byproduct, we get huge amounts of heat. And on a typical compressed air system, that heat is basically just expelled into the environment. Just if you've got an air-cooled compressor, it's blown out of the compressor room. If you've got a water-cooled compressor, that warmed cooling water will probably go through a heat exchanger and be blown out into the environment. So how can we reclaim that heat? Well, we can do that by using energy recovery systems. So all of that waste heat, we could potentially reclaim. And there's 2 ways of doing it. So we could, the simplest way is to, if we've got an air-cooled machine, is to take the warm air off our air-cooled machine and divert it into, for example, a warehouse next door. So that warm air is going in and helping heat our warehouse next door. It's a little bit limited. Firstly, it's seasonal. So in the summer, you won't be getting the benefits of your energy recovery. Secondly, it's very low-grade heat. So you can't transport that heat very far. Ideally, you want the user of that heat to be right next to where you're generating your compressed air. So it's very restrictive, very limited in its application. Another way of recovering the heat of compression is to convert that heat into hot water. And you can fit your compressor, you can also retrofit your compressor with options that will convert the heat of compression, convert that into hot water. Typically, that hot water will be coming off at 80 to 90 degrees C. And in a lot of industrial processes, having hot water available in that kind of temperature, so that's good quality heat, 80 to 90 degrees C. There's a lot of uses in a lot of industrial processes for that kind of heat. So we've just got some examples here. You could use it in a central heating system to help top up your central heating system. If you have got shower rooms, shower facilities, you could potentially use a system of heat exchangers, using that as an assist to using that energy as an assist to heat up your hot water. Probably the most common usage for energy recovery systems is to use the heat to basically go into pre-feed of your boiler water. So if you are using hot water or steam in your industrial process, you could use the energy off your from your compressed air system. You could use that to preheat the boiler feed water. And even if you can preheat by 10, 15 degrees C, that's going to save you a lot of energy in the long run. And we've got an example here of an energy recovery system fitted. In this case, it was a glass manufacturer. They only had a small compressor, 18 kilowatt compressor, and yet energy recovery was giving them some really good payback, especially in this era now of high energy costs. They were using the energy recovery in a floor heating system. That said, energy recovery, the application of energy recovery is very application specific. So as I said, if you can fit energy recovery, it's probably one of the best way by far of reducing your overall cost of compressed air generation. So investigate if you've got an application that you can use warm air or can use hot water. Okay, so that really, I've come to the end of my slides now. I'm going to hand over to my colleague, Jason Chapman, and Jason is going to go through efficiency and some efficiency techniques when it comes to industrial cooling systems. Okay.
Brilliant. Cheers, Oliver. Thank you very much.
I'll just stop sharing. There we go.
Yeah. And I'll start sharing my screen. Brilliant.
Oliver, quick question, and Jason, I've just had a message from somebody who registered but couldn't make it anymore. Are we okay to share the set of slides afterwards?
Yes. I'm certainly mine. Yeah.
Brilliant. Yeah. Thank you.
Yeah, no problem at all. So hopefully everybody can see my screen clearly now. Should be straightforward enough. Just to say thanks, Oliver, for the introduction to Atlas Copco and obviously our long history in research and development and the energy savings that we all look at across our divisions as such. So I'm moving on to the potential of carbon reduction and energy savings when we're talking about process cooling systems. So initially, what is a process cooling system? We're talking about systems that cover, working at the moment, bear with me 1 second, there we go. So a cooling system, there's various different types of cooling systems out there at the moment. So we've got industrial chillers for machine cooling and production cooling. Commonly, the largest systems will have HVAC systems, residential systems, unitary equipment for RTUs and standardization of components and things like that, and also large chillers for climate control. So as you can see on your screen there, we have circled the ones that fall into process cooling. And to be a little bit more specific, the area that's been highlighted in the white box there, this is where we're looking at on the process cooling side of things. So we're not discussing about HVAC, residential cooling, comfort cooling, or room ventilation of any type. It's purely down to production and industrial cooling of a process. So what is process cooling then? Well, initially, it is, as we say, it's a fundamental part and a consistent part and consistency requires for efficient production. Okay, an efficient system. If you've got an efficient system, increases throughput, it reduces downtime, and it increases your profitability. So what else is it doing? Well, if you've got an efficient system, it helps correct or helps ensure correct product quality. So your widget that's coming off the line at the end of the day is meeting all your quality checks, keeping your customers happy. So now a lot of these points, there's various systems out there that we can use. So you can see they've got different types of chillers, just as we are on compressors, from small units that almost like a filing cabinet size to large, almost container sized units that's based outside. Depending on the use and the type of unit, the footprint size, the weight, it depends where the locations are. So, but they all have one thing in common. Every one of these has a financial and environmental impact. So what do we need to consider? We need to consider the age of the system. Is the system old? Is it outdated for its needs? I know looking back at some of the poll questions early on, there's a few that came through there, obviously stating that the production or the manufacturing process has increased since your chiller system has been in place. So potentially what you are potentially doing there is using your backup system or running the system inefficiently. So you're running it flat out, you're not getting the cooling that you need, which, as we go back to the previous slide, could have a detrimental effect on your outcome of your production, your processes, or your widgets that are coming off the line that way. So, is the system old, new, and outdated? Has production increased? So, as we said before, so the chillers, coolers are running more than original design spec. Do you consider routine and regular servicing? If so, who maintains that system? Is it a professional body? Is it a professional subcontractor, or is it someone in-house? Obviously, there's benefits and there's flaws from every type of whoever's looking after the system that way. But as long as somebody's up to speed, they know what to look for, and they're not just looking at it and saying, "Oh, that'll be okay," because it's been okay in the past. It's not forced to be okay now, even if it has been in the past. So, as part of that, are routine checks carried out by the site teams if it's not down to a external body to come and check for you? Other things to consider then. Common one for us in this country is the environmental factors. Now, we are only a small country, but throughout this country, we've got various, obviously, degrees of weather, environmental impacts. So location makes a big direct impact on your chiller performance. Not just where they are in the country, but where are they based on site? Are they in direct sunlight? With that in mind, we also have to think about the seasonal impacts, local vegetation, pollen and debris. Are you next to a road? Are you next to a recycling plant or something like that? All these type of things need to be considered, especially this time of year at the moment, we get lots of pollen, tree pollen, things like that. These can all have a real detrimental impact on your chiller and cooler system, as they can on the compressed air as well, by clogging up your coolers. So this then brings us back to the regular and routine servicing and maintenance by on-site teams from day to day, to also maybe an external body that's coming to do these 6 months, twice yearly, or whatever the routine plan is. So what else we need to consider then? Let's look at the process use. Very similar to the compressor side of things, does all the system or all the process require the same cooling needs? Highly likely not. But are we then being inefficient by trying to cool it down to the most extreme of cooling, rather than having a specific point of use chiller for that process, especially if it's only a small part of the production itself? As I say, can point of use chillers be used? Okay. Temperature control units. So you might have a general system where you're cooling the entire system, but one line needs a bit of a warmer temperature. So instead of then further cooling for the old system, you could get away with a temperature control unit just for that one particular line, where you can raise the temperature up if need be. So what can we do? Okay, so system reviews. Let's look at the system. Chiller checks by professional teams. This comes back to one of the questions in the Q&A earlier about the compressed air as well. What can we do? Have your system checked out. If you don't know what you're looking for, ask the professional bodies to come and have a look. We can come in, do a complete survey, run through things and come up with suggestions. It might be a simple solution. From a compressor side, it might be a larger receiver. From a chiller side, it might be a point of use unit. We're not always talking big capital expenditure for a simple solution to get a bit of a payback on it. Okay, what can we do following from that? Production needs. Check your production needs. Have a look at your shift patterns. This once again ties into how Oliver was saying with the VSD types or the 2 shift patterns or the flat out loads. Have a look at your shift patterns. Reduced requirements. Okay, what does this mean then? From reduced requirements, is there any point where throughout the process you've got a skeleton crew on? You're only working 2.5 shifts a day. You know, between 12 and midnight and 4 o'clock in the morning, it's just a skeleton maintenance crew, something like that. If so, does your system still need to be running at full chat? Possibly not. It might do for production and cheaper costs for electricity during the evening, but we can ask all those questions. A professional body can come in, ask all these questions, do the check, and then consult with you there, which is the best ways forward. The next one we can look at is using things to our advantage. What can we use? Now, in this country, we don't have the luxuries of long summers or really harsh winters. So we can use nature to our advantage. For example, within the UK, which is quite surprising to a lot of people, the average UK humidity is 84%. That's average across the UK. Yes, down in the southwest and the southeast, humidity is lower compared to the northwest. But what else can we look at? And within the UK, we need to look at the temperatures. The average UK high annually is 14 degrees. Yeah, we get a couple of months where that goes above, where we've got to look at you know, the type of chiller system that we're using or how we use it. But for the rest of the 10 months out of the year, potentially we can use nature to our advantage, and nature's free. We don't have to do anything, it's just there, and we can just make the benefits of it. So what does that lead us into? How do we use nature to our advantage then? As we said in one of the poll questions, have you thought about free cooling adiabatic? We're going to discuss free cooling at the moment. So free cooling, what is this? Well, it's the method of using the ambient air temperature around the coolers and the chillers, and using fans rather than a refrigeration circuit. So it uses low energy cooling fans. It brings this in and it can save you up to 50% on your energy costs on running your chiller, just by using nature and a variable speed fan. So we're not using the chiller circuit, so we're not using the actual compressors within inside the chiller itself. We're just using a fan and moving the air across the coils. What else can we do? Well, as we discussed, we've got adiabatic pre-cooling. So pre-cooling is where we use a water system to pre-cool as you can see on your screen there, the bottom left-hand corner, the brown pads. It's like a cellulose pad. And as the air passes over these dampened pads, it then cools and then goes through the cooler. So therefore, the chiller circuit or your free cooling circuit does not have to work as hard to get the same output temperatures that you need. So as you can see on the actual pictorial there, so the warm air coming in, by the time it passes over the chiller pad, the adiabatic pads, reduction in temperatures before it reaches the cooler, so they're not working as hard that way as well. So using free cooling to our advantage, and what is the free cooling zone? As we said, it can reduce energy savings by up to 50%. So how does this actually look? Well, if we look at the graph there, the free cooling energy zone on the left-hand side is what's shaded in blue. So as the free cooling runs, the white line above the blue is where the normal chiller would be using, be running. The orange line that you can see is the free cooling zone. So as you can see, it reduces the amount of consumption in power in kilowatt hours quite significantly. And this is the zone we're trying to get to use advantage of, especially in this country. We can use, you know, it probably 8 months out of the year or so. And obviously by using nature to our advantage that way, we reduce the energy spend and also reduce the carbon impact. So on the next pictorial, you can see there the highlighted green zone is free cooling, 100% free cooling, which we can get for quite a few months out of the year. We then also got partial free cooling, and then obviously down to the actual compressor cooling only, which is the chiller side of the chiller. So by doing this, we are now obviously using simplified analytics of the compressor and the chiller itself. We can obviously set the system up so if it's not in 100% free cooling, it's then using partial free cooling. So the fans turn up and we can use adiabatic pads to run alongside it. Or if the temperatures are above a certain set point, we then just revert back to the chiller mode. Obviously, by it being above a set point, it means the chiller is not running all the time, which then refers us back to the energy savings and the reduction in the carbon impact. So to simplify this then, what we can see there is the hot water from your process comes back to the chiller, the cooler. It goes through a three-way valve, depending on the ambient temperature. It will either divert it through the free cooling coil, which is highlighted in blue in the picture all at the top. It'll either then go back into the circuit, or the motorized valve will divert it straight into the refrigerant cooling, depending on the ambient temperature. What is omitted from here, which I put on there, is partial free cooling. It's where obviously it can divert so much of the process through the free cooling, the off through the refrigerants. It's just getting the best of the system without running flat out on one or another. Adiabatic pre-cooling. So, as I said before, what is this? Bit of a magnified pictures there on the actual adiabatic pads. And how does this work? As we said, it increases the chiller cooling capacity at high ambient temperatures. So when we do have the hot months or the hot couple of weeks potentially that we only get in the UK, we can saturate these pads with normal water. There's no chemicals, no glycol, or nothing in it. It's just normal city water as such. So it just runs through. The air passes over it. It's cooled as it goes through the adiabatic pads, and then it coolers. It decreases the chiller energy consumption. So they don't have to run as hard because you're already pre-cooling the air. How does this work? Well, then it improves the entire unit efficiencies. And as we can see from the pictorial at the bottom there, once again, we've got the hot ambient temperatures coming in through the adiabatic pads, which are dampened and cooled, then obviously over to the actual condenser and out through the bottom. So examples of potential energy savings on the chiller system then. What have we got? So if you've got your factory using adiabatic pads or pre-cooling, this reduces your energy spend and reduces obviously the impact and the reliance onto carbon fossils and things like that, which ultimately saves you money and it saves your impact on the environment. Another good example as we move on there is an actual energy savings. As you can see from your screen, this is based in London, just as a scenario, but when a chiller or cooler company will come in and have a look, they'll look at your specific location, because as we said, such as in the northwest compared to the southeast, there is a variant of what we can use nature-wise to the best impact. But that can be all discussed and obviously reviewed by the experts coming in to do the chiller checks. But a great example there is obviously on your screens at the moment is using chiller mode for 650 hours a year. Okay, adiabatic modes, once again, depending, that's only about 176 hours per year. Not so much in this country, so because we don't have the extremes of high temperatures. But the best one we can utilize in this country is the free cooling mode. Majority of the year, 7,900 plus hours per year of free cooling. So we're using nature to its advantage. And that's based on essentially 8,000 hours, 8,760 hours a year, running 24/7 on the system. So that is basically 44%. So nearly half of your energy spend on your cooling or chilling system can be reduced by using free cooling, using nature to the advantage. So to summarize, let's have a look. Make sure we've got the correct system for your needs, the size, the type, and the age. If it was put in 7 years ago, 10 years ago, with the technology advances that we've all got nowadays, highly likely it's out of efficiencies compared to what you can get for the same or probably smaller footprint and a lot less impact with the environment and a lot less charge on the electricity costs. As I said before, weather is free. Let's use it. Use nature to our advantage. It doesn't cost us anything to use nature. Yes, the capital equipment does, but if we can use part of it, then that's our advantage. Service and maintenance. Make sure you've got a correct service plan and maintenance plan in place. It doesn't always have to be for an external body. Daily checks, weekly checks, especially this time of year, making sure that such as the coolers in your chillers are clear from debris. Things like people's not leaning things up against it. If they're outdoors, there's no wagons parked in front of it, stopping the actual cooling air getting to the chiller condenser coils itself. Don't take for granted that it's working efficiently. So if we look at the costs, the carbon impact, and your production, these all have a massive impact on your energy spend. What we want to do is work with you to reduce these. In summary, have a look, ask the question, speak to the professionals. So, any questions on any of that or the compressed air side of things? I see a few have come in now. I'll just stop sharing my screen at the moment.
Thank you very much, Jason and Oliver. Quite eye-opening, I must say. So we'll delve straight into the Q&A because we have only 5 minutes now. So there's one question here. Thank you for all these useful information. What do you think of pipes inside the factory? Are there any improvements on efficiency to make?
Yeah, it's definitely, it's one thing to look at is obviously depending on the amount of cooling capacity you need and especially where the pipe work is running as well. So if you're running from a cold environment outside and it's then passing through a warm environment and then back into the cold, you definitely need to look at lagging. Lagging can obviously depend on the type of lagging, where it is, how high it is up the wall, the ambient room temperatures. It can have an increase in cooling efficiencies, but anywhere between 2 and 25%, to be fair. So it's definitely something that needs to be considered.
Thank you. And we have another question from Manikanta Ravi. How much does a leak detection system for compressor system cost on average?
Good question. It's well, it's actually not a system that's fitted to the compressor. It's a service. So it's available from several different suppliers, certainly within the UK. I think all the major equipment manufacturers have got a leak detection service, and basically it uses a sonic type of instrument that the user will sort of do a walk around of your compressed air system and then find and tag the leaks for fixing. Rough cost, good question. Depends on the size of your system, I'm afraid. But there are many suppliers who will do that. Atlas Copco, obviously, being one of them, who will provide that type of service.
Thank you. And I think we